Welcome to Elementary Python for CBSE. Today we are going to discuss a new topic, that is Boolean Logic. In this topic we are going to learn different logical operations and logic gates, truth tables and how to represent Boolean function using truth table, various laws or postulates of Boolean algebra, and we'll design logic circuits using the logic gates. George Boole, the famous mathematician, developed the system of logic called Boolean logic. Algebra that deals with Boolean variables or Boole variables is called Boolean algebra. These Boolean variables, they are the binary valued quantities and can have values either true or false. These are called truth values. True is usually represented by the bit 1 and false is represented by the bit 0. The system works with Boolean variable very computably, as various elements of any electronic circuit can be represented using these true values, as they are two-state devices. High voltage may be represented by 1, low voltage represented by 0, and so on. Logical problems are binary decisions, and Boolean logic effectively deals with these Boolean variables. Any expression that have Boolean variables is called a Boolean expression or a Boolean function. So basic logic operations are AND, OR, NOT. Truth table is generally used to represent all possible values of the logical variables along with the result of the inputs for any logical expression. A truth table can be called as a table of values of truth functions. If any logical expression is always true, then it is called a tautology, and if the logical expression is always false, it is called a fallacy. Since each Boolean variable can have only two values, that is 0 or 1, any Boolean expression or function with n variables have a total of 2 power n possible combinations. Logic gates are the basic electronic circuits which operate on one or more input signals to produce an output signal. Various Boolean operations are performed in a computer using logic gates, and the logical operations can be represented using logic gates. So we will start with the basic logic operation NOT. The logical NOT operation, it represents logical negation. That means it complements the input. It is a unary operator and it can be applied to a single operand. For example, if we are taking an input, say A, then the result or output of this logic operation NOT is the inversion or the complement, that is A complement. So if the input is 0, the result will be 1. If the input is 1, the result will be its complement 0. This gate, which represents the logical NOT operation, is called the NOT gate or the inverter. Logical AND operation represents logical multiplication of the operands. It's a binary operator and can be applied to two operands. Dot symbol is used to represent logical AND operation, and the result is 1 if all the inputs are 1. Alternately, we can say if any of the input is 0, the result or the output will be 0. With two inputs, we can have 4 possible combinations: 0, 0, 0, 1, 1, 0 and 1, 1. And the AND operation between A and B is, for 0, 0 it will be 0, for 0, 1 it will be 0, for 1, 0 it will be 0, since at least one of the input in this case is 0, so the output is 0. But in the last case, the inputs are 1 and 1, so the output is also 1. The logical AND gate is used for representing logic AND operation. Logical OR operation represents logical addition of the operands. It's a binary operator, so it can be applied to two operands. That means it needs operands in either of its sides. This is represented by the addition symbol. The result will be true if any of the input is true, or the result is 1 if any of the input is 1. The output of the OR operation will be, for 0, 0 it will be 0, and for rest of the cases it will be 1 because any of the input is 1 here. Conversely, we can say if all the inputs are false, the result will be false, otherwise the result will be true. The logical OR operation is represented by the OR gate. We can represent any Boolean function using truth table. For example, suppose we want to represent the Boolean function x dot y. This is a Boolean function with two variables x and y. So we need two inputs. With two inputs, we have four possible combinations 0, 0, 0, 1, 1, 0 and 1, 1. Since x dot y represent logical multiplication, so the result will be 0 if any of the input is 0 and 1 when all the inputs are 1. Similarly, suppose we want to represent the Boolean function x plus yz. Yz means y dot z. It is known, obvious that yz represents y dot z. So it's a Boolean function with three variables x, y and z. So we need 2 power 3, that is 8 possible input combinations, which are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. For drawing the truth table, we need to represent all the inputs along with the output, and we can represent the intermediate Boolean expression y dot z. We need to find out the result. So y dot z is 0 dot 0 is 0, 0 dot 1 is 0, 1 dot 0 is 0, but 1 dot 1 is 1, 0, 0, 0, 0, 1, 0, 1, 0, 0 and 1, 1, 1. Now we add x and yz. If any of the input is 1, result is 1. So in these three cases, both are 0, both the inputs are 0. So these are 0. In this case, the 0 plus 1 or 0 or 1 is 1. 1 or 0 is 1. 1 or 0 is 1. 1 or 0 is 1. 1 or 1 is 1. So the result, that is x plus y dot z, is 0, 0, 0, 1, 1, 1, 1, 1. We can represent the Boolean function a complement dot b plus c. It's a Boolean function with three variables, that is a, b, c. So we require three inputs a, b, c, which will have 8 possible combinations. We need a complement, so we have found out a complement. A is 0, 0, 0, 0, 1, 1, 1, 1. So the complement is 1, 1, 1, 1, 0, 0, 0, 0. Then we need to find out b plus c. OR operation means if any of the input is 1, then the result will be 1. So in this case, we have 1. Here also we have a 1. Here also we have a 1. Here we have a 1. Here we have a 1. Here we have both inputs 1. So b plus c will be 0, 1, 1, 1, 0, 1, 1, 1. And a complement dot b plus c. So we will multiply this a complement with b plus c. If any of the input is 0, the result will be 0. So here in this case, the output will be like 0, 1, 1, 1, 0, 0, 0, 0. This way we can represent any Boolean function using truth table. NAND and NOR gates can be designed from AND and OR gates by complementing their output. So NAND gate represents not AND, logical negation of AND gate, and NOR gate represents logical negation of the OR gate. This is a shorthand representation for NAND gate, and this is a shorthand representation of NOR gate. So with NAND gate, the output will be the complement of the AND gate. For AND gate, we have the output as 1 when all the inputs are 1. So for NAND gate, we have the output as 0 for all inputs to be 1 and 1 in rest of the cases. Similarly, for NOR gate, we have the output to be 0 for all the inputs to be 0 and 1 for any of the inputs to be 1. In case of OR operation, the output is 1 for any of the input is 1 and 0 when all the inputs are 0. So with NOR gate, this will be reversed. So NOR gate will have output 1 when all the inputs are 0 and output 0 when any of the input is 1. This NOR gate and NAND gate, they are also known as universal gates, as any logic circuit can be designed using NAND gate and NOR gate. So we will see how we can design NOT gate and AND gate and OR gate the basic logic gates using NAND gate. We know a NAND gate has two inputs. For input 0 0 the output is 1, and for input 1 1 the output is 0. When we provide the same input 0 and 0, so 0 dot 0 is 0, which complement is 1, so we get a 1. So this, by joining the both input to a single input of a NAND gate, we can get the NOT gate. So this circuit represents NOT gate designed using NAND gate. If we provide 1, both input will be 1. This is 1 dot 1, so complement of 1, which is 0. Similarly, since NAND represents NOT AND, so we can get AND gate just by complementing the result of a NAND gate. As per involution law, we know that complement of a Boolean variable is the Boolean variable itself. So when we complement, this is a NAND gate, when we input this, it will complement, the result is AND gate. Similarly, we can design a OR gate. For one input we'll use a NAND gate, so this gives the complement of that input. Suppose the input is A, then this will get A complement. Similarly, if the input is B, we can get the B complement. When we apply this input to another gate, then we get complement of A complement or B complement, and by applying De Morgan's law, we can find that this is involution of A plus involution of B, which is A plus B. So this gives the output as OR gate. So we can say this is an OR circuit designed using NAND gates only. This way, any Boolean function or any logic circuit can be represented or designed using NAND gate. Similarly, we will see how we can represent basic logic circuit using NOR gates only. So this is the same design. We have just used NOR gates here, and we have connected both the inputs of a NOR gate to a single input, so that when we provide any input, both the inputs will have the same value. For example, suppose we provide A as a single input, then both will have A, and the output will be A plus A complement, which is A complement. So if we input 0, we get 1. If we input 1, we get 0. So this is behaving like a NOT gate. So this circuit represents NOT gate, which is designed using NOR gate only. Similarly, if we complement NOR gate, then we get OR. So OR gate can be easily designed by just connecting a NOR gate to the output of another NOR gate. So for the second one, both the inputs will be A plus B complement, and this will be the complement of A plus B complement, which is A plus B by involution law. We can get the complement of A and B by using two NOR gates, and when we provide this inputs to another NOR gate, then by De Morgan's law we get A dot B. So this circuit represents AND gate, which is completely designed using only NOR gates. There are two more gates, exclusive OR or XOR and XNOR. Exclusive OR indicates that when either of the input is 1 or true, then the result is true. In contrast to the basic OR operation, which is also called inclusive OR, in which case when all the inputs are 1, result is also 1. But the difference of exclusive OR is, in this case the output will be 1 only when any of the input is 1, not all the inputs. So it excludes the value for all the inputs. That is why it is called exclusive OR gate. If we find out the expression, then we can say that this may be represented as A complement, and this is B, this is A, and this is B complement. So if we find out the sum, then this is A complement dot B plus A dot B complement. So XOR gate can be represented by the Boolean expression A complement dot B plus A dot B complement. This is the representation of exclusive OR gate. XNOR gate is the logical negation of XOR gate. So in this case, the output will be true if all the inputs are either true or either false. So the output is 1 for all zeros and all ones. Otherwise, if either of them is 0, either of them is 1, the result is 0. This is a logical gate representation of XNOR gate. We may also derive this XNOR gate by complementing or negating the XOR gate and applying the De Morgan's law. In Boolean algebra, there is a principle of duality which states that we can derive a Boolean expression from another Boolean expression called its dual by changing the or to and to or, and replacing 0 with 1 and 1 with 0. X plus y complement dot z. The dual of this expression is x. In place of plus we will have dot, in place of dot we will have plus. So this is x dot y complement plus z is the dual of x plus y complement dot z. Similarly, if an expression is given as x plus 1 equals to 1, the dual of this expression will be obtained by replacing plus with dot and 1 with 0. So the dual of the expression is x dot 0 is 0. We can also verify them using truth table. Similarly, dual of a plus b complement is a complement dot b complement. That is, in place of plus we will put dot. So a dot b complement is a complement plus b complement. Some basic theorems of Boolean algebra. X plus 1 is 1. Whatever may be the value of x, whether it is 0 or 1. So if it is 0, then 0 plus 1 is 1. If it is 1, then 1 plus 1 is 1. Logical multiplication with 0 of any Boolean variable results 0. So 0 dot 0 is 0 and 1 dot 0 is 0. X dot 1 is x and x plus 0 is x. That means 0 is the additive identity and 1 is the multiplicative identity. So whatever may be the value of x, if it is multiplied by 1, then the result will be the Boolean value. So if the value of x is 0, it is 0. If the value of x is 1, it is 1. Similarly, when we add with 0, the result will be the value of the Boolean variable. So if it is 0, then the result is 0. If it is 1, the result of logical addition with 0 is 1. If we add a Boolean variable to itself, the result will be the Boolean variable itself, or we multiply it with the variable, then the result will be the Boolean variable itself. For example, 1 plus 1 is 1 as well as 1 dot 1 is 1. 0 plus 0 is 0 as well as 0 dot 0 is 0. Then the next one is called involution law. If we find the complement of a Boolean variable, then the result will be the Boolean variable itself. For example, if we find a complement of 0, it is 0 again, because 0 complement is 1 and 1 complement is again 0. Similarly, if you find the complement of 1, it is 1, because 1 complement is 0, again 0 complement is 1. Then laws of complementation say that the logical addition of a Boolean variable and its complement results in 1, and the logical multiplication of a Boolean variable with its complements results with 0. So if x is 0, then 0 plus x complement, that is 1, is 1. Similarly, if x is 1, then the complement of 1, that is 0. The logical addition with complement of 1 is 1. Whatever may be the value of the Boolean variable, when we add it to its complement, the result is always 1. The complement of the logical multiplication of 0 with its complement 1 is 0. Similarly, logical multiplication of 1 with its complement 0 is 0. Then we have commutative law. We have verified commutative law as well as associative law using truth table. So commutative law states that a plus b is b plus a and the dual is a dot b is b dot a. So here we have verified that result of both a plus b and b plus a are same, a dot b and b dot a are same. Similarly, associative law states that a plus b plus c, if we have adding three Boolean variables, then we may pair them from any side. That means either we can first add a plus b, then add c, or we add a to b plus c. The result will be the same. Here we have shown how we get the same result. Similarly, this is true with multiplication, logical multiplication as well. That means when we are multiplying three Boolean variables a, b and c, then the result of multiplying a dot b with c or a with b dot c remains the same. So this is the result of associative law with respect to multiplication. And distributive law, a dot b plus c results in a dot b plus a dot c. Similarly, the dual of the expression is a plus b dot c, and this is equal to a plus b dot a plus c. We have verified the result of distributive law using truth table. So the first part, a dot b plus c and a dot b plus a dot c, we can see that the result of both are same, a plus b dot c and a plus b dot a plus c. The result of both are the same. Then absorption law, which states that x plus x dot y equal to x. We can see here that the second variable in this case is absorbed. Similarly, the dual of the expression is x dot x plus y, which is x. Again, we can find that y has been absorbed here. So we have verified it using both truth table as well as algebraically using the laws of or postulates of Boolean algebra. So we can see the result of x plus x dot y is equal to x. Similarly, x dot x plus y is again equal to x. Algebraically, we can say that x can be written as x dot 1 because logical multiplication with 1 results with the same variable, and then we can use the distributive law to pair up 1 plus y, and then we know that 1 plus y is 1. The result of addition of any Boolean variable with 1 always results in 1. Again, x dot 1 is x, so x plus y is x. Similarly, x dot x plus y, we can apply the distributive law to find x dot x plus y equal to x dot x plus x dot y. Now x dot x is x, and when we again apply the distributive law, we get this can be written as x dot 1. So we can have x dot 1 plus x dot y, which is x dot 1 plus y. Again, 1 plus y is 1, so x dot 1 is x. There is another law, x plus x complement y. In this case, the complement will be absorbed and the result will be x plus y. We have again verified it using truth table. So we are having x plus y and x plus x complement dot y. We can find the result of both the expression is the same. Similarly, we can prove it by applying distributive law to LHS left hand side. So x plus x complement dot y can be written as x plus x complement dot x plus y, and we know x plus x complement is 1. When 1 is multiplied logically with x plus y, then we get x plus y. De Morgan's law states that the complement of logical addition of two variables is the logical multiplication of their complements. Similarly, the complement of logical multiplication of two variables is the logical addition of their complements. We'll verify them, one of the law using postulates of Boolean algebra, that is algebraically, and another using truth table. We know that by the law of complementation, logical addition of a variable and its complement results in 1, and logical multiplication of a variable with its complement results in 0. So suppose we say that x plus y is a, then a complement is x plus y complement, and we can say that the complement of x plus y is right hand side x complement dot y complement if it satisfies the laws of complementation. That means the variable with its complement should result in 1, and the variable multiplied by its complement should yield 0. If we are claiming that x complement dot y complement is complement of x plus y, then their logical addition should result in 1 and their logical multiplication should result with 0. Suppose this represents a, then by applying distributive law a plus b dot c, we can say a plus b dot a plus c. So we have x plus y plus x complement, x plus y plus y complement. Now we will keep the variable and its complement together applying commutative law. So x plus x complement and y plus y complement we get, and by applying laws of complementation we have logical addition of a variable and its complements results in 1. So x plus s complement is 1 and y plus y complement is 1. 1 dot 1 is 1. So here we find that x plus y, when logically added with to x complement dot y complement, it resulted in 1. Similarly, the second part we will see when we find the logical multiplication of x plus y with x complement dot y complement. First we will apply commutative law. A dot b can be written as b dot a. So we have written x dot y complement dot x plus y. Then we will apply distributive law. So x complement dot y complement dot x plus x complement dot y complement dot y. Now again we will pair up the variable and its complement. So by applying complementation law, we find x dot x complement is 0 and 0 dot anything is 0. Similarly, y dot y complement is 0 and 0 dot anything is 0. So 0 plus 0 is 0. So from part A we have found that x plus y, when logically added with x complement dot y complement, resulted 1, and when logically multiplied with x complement dot y complement, it resulted in 0. So we can claim that x complement dot y complement is the complement of x plus y. Here we have verified x dot y complement equal to x complement plus y complement using truth table, and we can find that the result of both the expression is the same. Logic circuits for any Boolean expression or function can be designed using the various logic gates like AND, OR, NOT, NAND, NOR, XOR, etc. We will see how we can design the logic circuit for a given Boolean expression. Suppose the Boolean expression is x plus y dot x complement dot y complement. Then we have two inputs here, so we'll take two inputs, then represent each intermediate expression using the corresponding logic gate. This is a logical addition, so we'll use the OR gate to represent logical addition. This is logical multiplication of the complement of the variables. So first we have to find out the complement using NOT gates, and this is y. From y we have taken an input, so this is y complement. From x we have taken input, so this is x complement, and we have used an AND gate to find the logical multiplication. So this represents x complement dot y complement. When we apply these inputs to another AND gate, we get the output of the given Boolean expression, x plus y dot x complement dot y complement. So this logic circuit represents the given Boolean expression x plus y dot x complement dot y complement. Conversely, we can derive any Boolean function from the given circuit by writing the different inputs and the intermediate expression. For example, the inputs are x and y. This is an AND gate, so the intermediate output will be x dot y. Similarly, this is an input from the input x, and a NOT gate is used, so this is x complement. This is another input z, and NOT gate is applied, so this is z complement. This is an AND gate, so the output of this will be x complement dot z complement, that is the logical multiplication of both the inputs. Then an OR gate is used. Output will be the logical addition of the inputs, that is x dot y and x complement dot z complement. So the final Boolean expression is x dot y plus x complement dot z complement. That's all in Boolean algebra. Thank you.